Okay. On those worksheets where you see HG only, some of those notes date back to the days where you had higher grade and standard grade. HG was for higher grade pupils only. You're higher grade. There's no standard grade. Standard grade was like the equivalent of maths literacy to maths. You wouldn't get one with a question where you had to find the R value. You'd get one where Q was. And in fact, at standard grade level, you probably wouldn't be asked to do the ratio and proportion type of thing. You would just be given, this is the charge, that's the distance apart, calculate the force, use the formula. That would have been typical standard grade. Higher grade, you had to be able to think and apply your knowledge. Okay, right. We're now starting off with a new section of work. Still falls under electricity, very much part of electricity. I will give you notes, so you don't have to take down everything that I'm putting up here. But I don't want to give you notes now, I want you to listen. Electric fields. Any suggestion? What do you think an electric field is? But like an astroturf, but runs on electricity. Like a foosball thing. Air table. But with a little bit of static electricity, so it floats on this. Who of you have ever seen an electric field? None of you? None of you ever played with one? Okay, let's just do a bit of revision, okay? First of all, force fields. Who of you have ever worked with force fields? None of you. You only see it in sci-fi movies. So Jonathan, you reckon you putting a blob of spit on your hand and then moving your spit towards someone's field, that generates force. That's a non-contact force. And if I had to blow my nose with my hand and then just sort of say, that would also, okay, no, but that's not the type of force field that we're talking about here. Star Wars, talk about force field. Oh, that. Okay. The electromagnetic field. Do you know what an electromagnetic is? That's light. Is there a light field around the Earth? You thought there was. No, we're not a sun. We don't glow on our own. We reflect other light off us. So there's no electromagnetic force field around the Earth. You people have all worked with force fields. Who of you, in your primary school years, you must have worked with force fields? Magnets. Okay? You know of two types of force, two basic categories of force. What are the two basic categories of force we were taught this year? You got your contact forces and your non-contact forces. Give me an example of a contact force. That's the easy one. Punch someone or push something or hit something or whatever it is. So as soon as there's contact, so I take this pencil bag and I move it across here. I've applied a force, the pencil bag moved. So that's a contact force. Or I hit Miller and she goes flying, I've applied a force. Or I pull a tooth out of someone's gum. If I'm a dentist, I've applied a force and I've achieved something. Or I take a ball of putty and I squeeze it. There's contact. Those are the contact forces. I can give an example of a non-contact force. What? A positive and positive magnet. I've never heard of positive and negative magnets. North and a south magnet. Okay, so if I had, let's say this was my south magnet. Do you get a south magnet? You get one magnet that's got a south pole and a north pole. but you don't get a south magnet, okay? But let's say you had a South Pole, North Pole magnet, and you had another South Pole, North Pole magnet. Imagine that this here is your South Pole, North Pole magnet. Now bring the two South Poles together. What will they do? They will repel, okay? And the two North Poles also repel. Turn it round, they will attract. Okay, now, was there any contact? Is there a force before they come into contact with? Yes, they don't have to be in touch with each other, but there's a force. There's an attraction force, or if I turn it away, there's a repulsion force. Okay? Anyone tell me why? How does this force act if there's nothing linking them? What pulls them together? The force field. Okay. And in primary school, you were taught about a magnetic force field. Okay? So, examples. The first one is the magnetic force field. You all know about it. You've forgotten about it from primary school days. How did you see what a magnetic force field looked like, Jacques? But what did you do to know what the pattern looked like? What does the pattern around a magnet look like? You've got those lines that run like a rugby ball. How do you know? Did your teacher do it for you? What experiment did you do in primary school? Nikita? And then you tapped the paper and the iron filings all fell into that beautiful little pattern. So if that was your magnet under the paper, north, south, your magnetic field lines ran from north around to south, from north around to south. That's a simplification of it, but always from north to south. Out of north, if I had space, around into south. Out of north, if I had enough space, around into south. Right. Now that was a magnetic force field. Now what would happen if I put a piece of iron there? Anyone tell me what would happen to that piece of iron? What would happen to it? It'll be attracted to the magnet. Which way will it experience a force? It will actually experience a force in the direction of the magnetic field line at that place. If I had to put a piece of iron there, it would experience a force in that direction. Obviously, as it moves in that direction, the field line changes, so it experiences a force. Okay. Strictly speaking, I shouldn't be using a piece of iron. I should be using a what? A compass. I had to put a compass there, and the compass there. What would happen if I had to put a compass here? Which way would it experience a force? In that direction there that the line is pointing at that stage. So can anyone tell me what is a magnetic force field? Is it a flat thing? Is it 3D? Is it on top of the magnet as well and underneath the magnet? Yes. Okay. So a magnetic force field is an area in space. Now what do I mean by in space? Out of space. Anywhere. Could be on your table in front of you. That's area in space, okay? In other words, I could just leave out the word in space. It's an area. Is a place, right? Where a magnetic object experiences a what type of force? a magnetic force. Okay, so you've got a magnetic object experiencing a magnetic force. Yes? It doesn't ever end. It extends. And what would happen if I had to put a compass here? Shoot to the closest line. Are those lines really there? No. Give me an example of something else that we use to explain things with lines when those lines don't really exist in real life. Sorry? Lines of longitude and latitude. If you had to walk around the earth, would you see these big painted lines? Oh, this is the line of 20 degrees south. Okay? You don't see lines of longitude and latitude. What other lines don't you see? What lines? The ones demarcating energy level 1, energy level 2. Yes, they don't exist. What? Electron paths. Yes, those lines don't exist. But one that is very, very often used. Everyone uses them somewhere along the line. In geography, you use them a lot. What? No. Map lines. What do you mean by map lines? You still call them map lines? Grid lines. No, I'm not talking about those. No. Contour lines, people. Who of you have ever gone hiking? Now, when you climb up a hill, the lines are quite steep on the ground, aren't they? Every 2 paces you see a line. Oh, this is really steep. But when the path is very gentle, you've got to walk about 100 paces between every line that's painted there. You agree? You do agree, Luther? I'm so pleased. Where do you go hiking? Right. In real life, there aren't things called contour lines on the ground. It is something that we use on maps to help us understand the shape and the steepness of slopes. The same applies to magnetic field lines. You don't see lines around a magnet. Okay? Even if you put paper on it and sprinkle iron filings, iron filings align themselves into shapes, but they're no lines. Those lines are just to help us understand a little bit better. Okay. The other thing is if you have a light, let's say you had a light bulb over here, we label it like that. What radiates out from that light bulb? Light. And how do we show light in science? With rays. Okay, beautiful. Rays coming out from there. So those rays carry light. So what happens if your eye is there? Pitch dark. No light. Okay, we know that light doesn't really travel in rays. It's a way that we explain it on paper. But there's no such thing as light rays. Okay? There's no such thing as contour lines on the ground. Obviously on maps, yes, you'll get them, but on the ground you don't get them. There's no such thing as these lines around a magnet, but we use them to explain magnetic fields, okay, magnetic force fields. All happy with that? Okay. Another type of force field that you have all worked with it's also a non-contact force, but we deal with it often. Gravity. So we've got gravitational force fields. So you've dealt with force fields before. It's not a new concept. We just haven't labeled it as such. We didn't tell you that you were being taught about force fields. So where's the first gravitational force field that you've all been led to understand? You yourself, you didn't know there was a force field emanating from you until I told you this year. But before that you knew about gravity with regards to what? What with regards to? The planets. Which was the only planet you knew up until the Earth. Okay, so here's the Earth. Right? And how do the force field lines run now? Do they also look something like this? Like that? They all run inwards like that. So yes, if you stand between these lines, you'll float. There's no gravity acting on you. Right. That's your gravity force field, gravitational force field. Now, what would happen if I had to put an object there? Which way would that object experience a force? To the center, to the surface of the Earth, or to the center? It would experience a force towards the center of the Earth. If I had to put an object there, it would experience the same force. Okay. So who can give me a definition of a gravitational force field? Carry on from this one. Is an area, to keep it correct, in space. Some textbooks talk about a region in space. Regions sound like specific areas. So it's a place, okay, where? What type of object? Where an object with mass. What type of force is it experiencing? Experiences a gravitational force. Yes. Right. So an object with mass. So that little dot that I put over there would be an object with mass. If I had to put an object over here, would it also experience a force upwards? Yes, towards the center of the Earth. An object with mass. So right, you've now learnt about how many types of force field? 2. You didn't know you knew this. Okay. All happy? Fine. Could you give me a 3rd type of force field? They're staring at you people. An electric force field. Okay. So number 3 would be an electric force field. Now, what did you find a magnetic force field around? A magnet. What did you find a gravitational force field around? Something that had mass. So do you have mass? Do you have your own gravitational force field? Yes, you do, and hence you can attract things towards you. Because you're so light, the attraction will be extremely weak. A planet like the Earth is pretty big, the attraction is a lot stronger. Okay, the question was raised here, do you get objects that don't have mass? No, electrons have got mass. Practically no mass, but they do have mass. Dust. They've got mass. What? Light. Gas has mass, yes. Does light have mass? Does light, light is a particle. A light particle is called a photon. That's a light particle. Does a photon have mass? No. Does a photon get attracted in a gravitational field? So if I shone a beam of light from the moon or from the sun to another planet, would it be attracted to the Earth? Would it fall to the Earth? Yes, it would. Okay, light is extremely weakly affected by gravity. Einstein was able to prove that, believe it or not, even these photons which have practically got no mass, but because of their movement, they start taking on mass. Okay, or they seem to behave as if they have mass. That light can be bent due to gravitational fields of planets. Okay, so you would not pick it up, but there would be a slight bending. Okay, what else can be affected by gravitational fields? Time. True. Yes, gravitational fields affect time as well. In fact, a number of things affect time. One of the big things that affects time is speed. So if you're traveling at a very, very high speed, what happens to time? It slows down. Is that just a rubbish from movies that you watch? Or is that true? What type of movies do you watch that you think it's true? It is true. I don't understand much of it at all, to tell the truth, but time can slow down. If you could travel at the speed of light, time would stop. You wouldn't get older. If you could travel faster than the speed of light, you'd go backwards in time. Now that sounds nice. The problem is you're going to put on a lot of weight. Because Einstein also proved that as you go faster and faster, your mass increases. You don't get bigger, you just get heavier. So if you were standing on a scale and you were going faster and faster and faster, you'd see, oops, I'm no longer 60 kilograms, now 70, 80, 90. As you picked up speed, your mass would increase. And as you approached, no, you can't lose weight by slowing down anymore because you people are absolutely sedentary. Okay? So slowing down won't be a good way to lose weight. Let me just lie. Check your weight on that scale. No, that wouldn't work. But as you approach the speed of light, what would your mass become? Infinite. Your mass would become infinite. This is not part of this work, it's just an interesting thing. Your new mass, we will call it m dashed, your new mass, is equal to your old mass divided by the speed of light in a vacuum minus the speed at which you traveled. So this is a very, very big number, that's c. Okay? But when you approach the speed that you're traveling, once this speed is equal to c, what does your denominator become? 0. And what's the 11th commandment? Thou shalt never divide by 0. Because if you divide by 0, your answer becomes infinite. Right. Okay, so your mass, your new mass, becomes infinite. You put on so much weight, it never ends. Okay? If you travel at the speed of light. So unfortunately, people, that's the price you pay for traveling at the speed of light and stopping time. Do you want to never age? But you are so gross, you're so big, and remember, you don't get any bigger, you look exactly the same. So you can be as skinny as anything, but you'll weigh more than anything else in the universe. People will be scared of you. Seriously. Not only that, what happens is your mass increases. Your gravity increases. So what happens? You become the center of the universe. And everything gets attracted to you. Planets. Okay? That is what would happen. So it's clearly something our minds can't deal with. But this is all true. This is all true. Yeah. Yes? Then you go backwards in time. Yes. I know, it won't. You'll be ahead of time. So if I travel so fast that I go back to yesterday and I stop, I'll be in yesterday and I'll go through yesterday again. And I'll wake up this morning again. I'll never be able to, unless I go backwards at the speed of light. Then I can move forwards in time. Right? So if you think about it, if I clap my hands, how did you see me clapping my hands? Yeah, you saw them clapping, but what made you see it? Light on my hands reflected off in all directions and traveled in all directions, and you all saw it, didn't you? My hands coming together. So you saw that light. Now, do you agree some light left through that window there and is headed off into the atmosphere? In fact, it's now left the atmosphere. It's just going past, it's heading towards the moon at the moment. It's going to miss the moon. It's going to just shoot out into outer space. It should be quite a way off by tomorrow. But if I could take off and chase that light, and if I could run at the speed of light and faster, I would catch up with it. You agree? And then I'd be able to see myself, as I was 5 minutes ago clapping my hands. So you'll be able to start seeing things, but you've got to travel at the speed of light to be able to do that. And they say you won't just see things, you will experience things. But it's certainly in our situation it's not possible. Yes. Yes. No, your mass recedes to a massive negative mass. Yes. So, do you get negative mass? Yes, you do. It's called antimatter. And it's not just a science fiction thing. You get antimatter. And if you take a matter particle with its equivalent antimatter particle and you put them together, there will be a release of energy and nothing. They disappear. Your antimatter and your matter disappear. They neutralize each other.
The moment that you start having particles in human life, no matter then you are technically antimatter, and the moment you touch anything,
Or the same out of flesh and bone.
out of flesh and bone.
So all that stuff that gets attracted to you because your mass is so heavy that it disappear fast, because it's going to disappear. Yeah, all of those implications start applying. Okay, thank you. Let's move on. So, we've said that not all particles have mass. Okay, light, for example, doesn't have mass, even though in extreme situations light can be affected by gravity, because even light photons do have mass of a certain extent. An electric force field. Now, what did you find a magnetic force field around? Around a magnet. A gravitational force field around something with mass. What will you find an electric force field around? Something with charge. So let's take a charged particle, a positively charged particle as an example. Around that positively charged particle, you will find field lines. And which way do those field lines run? Outwards. Remember, you don't really find the field lines. They're just a means for us to understand electric fields a little bit better. All right, there we go. And if that wasn't a positive particle, if that was, let's say, a negative particle, what would it look like? They would look exactly the same, but they would flow inwards. Without the little kink in the last one. Okay, right. All happy with that. What's our time now? We've got 5 minutes. Okay, who could give me a definition of an electric force field? You see the first line. An electric force field is an area in space where a charged object experiences a... Stop giggling, please, and talking. What type of force? What's the other name I gave to an electrostatic force? A coulombic force. So a charged object experiences a coulombic force. Now what would happen if I had to place a positively charged object there? In which way would it experience a force? With the line or against the line? Against the line. So the line's running to the right, do you agree? So you're saying that thing's going to be attracted towards there. Doesn't positive attract positive? No, in fact it repels. So a positive particle will experience a force with the line in the same direction. However, if that was a negative particle, there you are, there's a negative particle. That will experience a force, not towards, we say in the direction of the line. That will experience a force that way. Where would that negative particle experience a force? What's the rule I said? Negative experiences a force? No. Positive experiences a force with the line. So negative particles will always experience a force against the line. So that negative particle there will go that way. And we know negative repels negative, isn't it? Right. Now, why don't we just say positive attracts negative and repels positives? Wouldn't that be easier? Yes or no? Okay, that's what you were meant to say. Let's prove that you're wrong. Okay, what would happen if I had a positive particle there and a negative particle there? What would my force field lines look like? From the positive to the negative, because we know they run out of positive and into negative. So to run something like that. This line that was originally coming out that way, where would that one go? Where? Like straight to the negative. So to do like a parabola. Like that. And this one here. And this one. It actually gets attracted around. And that one. That one. Around eventually. Right. So that's the electric field around a positive particle. That's the electric field around a negative particle. This is the electric field between a positive and a negative. And what would happen if I had to put a positive particle there? Which way would the force be that it experiences? At that point, the force would be in that direction, at the tangent to the line. At that point there, positive, it would experience a force, the tangent to the line. If I had a negative particle and I put it there, sorry, negative particle, that's the tangent to the line at that point. Do you agree? Obviously, as it moves, it follows the line around. When I see you tomorrow, we'll look at the shape of a few other electric force fields. I want you to remember, stop packing away now. You to remember an electric force field is a region in space or an area in space where a charged object or a charged object experiences a coulombic force. We take it from there tomorrow. Thank you.